if it is compounded every possible moment that can be possibly compounded, we call that compounded continuously. Our equation is f of t is equal to p to the rt. P is still our principal amount, okay, our initial investment, whatever it is, our loan amount, whatever it is. E is the natural exponential, okay, it's that number that we've been using, that 2.76 whatever, okay, you just use the button on the calculator. You can't see this, I'm sorry. Okay, R is still our rate as a decimal. And then T is still the number of years, or as long as your units agree with what the rate was given as. Okay, if it said at a rate of 2.7% per day, then your T is in days, but most of the time it's given per year. Okay, so PE to the RT, that's the formula you use when the word continuously is involved in the word problem. So this first example says $500 is invested in an account that compounds continuously. So I know that I'm using PE to the RT. That's the only time I use this formula. Any other time, I use the formula we were just using. At a rate of 1.5%, how much will be in the account after 4 years? So 500 is our P, our rate is 0.015, our T is 4 years, so F of 4 is equal to 500 times E raised to the 0.015 times T, which is 4. And again, we're plugging into our calculator. The good thing about this equation, or this formula, is that when you do the E in your calculator, second, and the natural log button, it automatically starts your set of parentheses. So you don't have to add them in there. It automatically starts it for that exponent. It's one less thing that you have to remember. So after these 4 years, there will be approximately $530.92 after this compounded continuously action goes on. Okay, let's look at another question similar to this. Any questions about that one? Good. Okay. Second example. $7,500 is invested in an account that compounds continuously. So again, here's our P. Compounded continuously means that we use PERT. That's usually what I call it. PE to the RT, PERT. Here's a shampoo called PERT, by the way. At what rate, so they want to know R is our unknown here, did the account compound if there is $10,000 in the account after 10 years? So T is 10. $10,000 is our F of 10. It's how much was in the account after those 10 years. So they've given us some different information here. So let's use that. If there is $10,000 in the account after those 10 years, our initial investment was $7,500. E to the R, we don't know R, times T, 10. So we're solving for R. R is stuck in our exponent. What should we do first? Divide by the 7,500. We get rid of anything around our exponential before we can get into that exponent. So let's see here. Cancel the zeros. 100 over 75. I like fractions. 4 over 3. 4 over 3 is equal to E to the, I don't like R times 10. I'd rather write that as 10R. All right, what did we do last week when we got to this point? If our variable was in the exponent, how do we get it out? Okay, Can we make 4/3 and E have the same base? No. Okay, so what was our other option? Log form. Okay, when we get to this point, we put it in log form. Okay, when you have an exponential, your variable stuck in the exponent, you have to put it in log form. What log do we use with E? The natural log. The ln of 4/3 is equal to 10R. Remember, we can check it. Use your swoop. The base of the natural log is E. E to the 10R is equal to 4/3. Okay, so we have the same expression. We just flipped it around. What's our last step in solving for R? Divide by 10. That's the exact answer. I don't want the exact answer. I need to know the rate. I need the actual decimal here. So natural log of 4/3, close my parentheses, divided by 10. Okay, I get 0.0287 is R. That's in decimal form, so I can convert it to a percent by moving it over 2 places. So 2.87%. Okay, so most all the problems we've been doing so far, we've been plugging in. Well, sometimes you have to solve for something inside the formula. So that's what we're looking at there. All right, while we're on that train, let's do this problem. Okay, I don't know why I started over at 1. This should be 3. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Okay, so we start with 100. Let's just make our exponential model here. We start with 100. It's exponential growth, right? Exponential growth. We're not compounding. Compounding is only with money. Okay, this is exponential growth. So it's 1 plus, what's our rate? We're doubling every hour. Something doubles every hour. Okay, we're going to end up with a 2. Okay, but in terms of a rate, in terms of a percent, you have 100% more, right, than you did before. So if we turn 100% into a decimal, that means R is going to be 1 to the T. Okay, this is just going back to our basic exponential growth. So this is our model. It says predict when the number of bacteria will be 350,000. So that's what our model is going to equal. 350,000 is equal to 100 times 2 to the T, because 1 plus 1 is 2. What do we do first? What do we do first? Divide by 100. Okay, divide by 100. So that leaves us with 3,500. Is equal to 2 to the T. Our variable stuck in the exponent. What do? We don't divide by 2 because we're not multiplying by 2. We're raising 2 to a power. Log form. Log base 2 of 3,500 is equal to T. Y'all did really well on this quiz. Why have we forgotten already? Yeah, because we didn't really learn it. We just crammed it long enough to get through that quiz, right? So we have to use change of base to get this value out of our calculator. So the log of 3,500 divided by the log of the base, which is 2. So that's approximately 11.77. What's our units here? Hours. That's kind of scary. We start with 100 bacteria They double every hour, and after not even 12 hours, there's 350,000 bacteria. Exponential growth is fast, y'all. It really is. Exponential growth is very, very rapid. It just exponentially increases. Thus, it's called exponential. Okay, so get another one. This is not a doubling problem. This is a half-life problem. Another application of exponentials here. Suppose the half-life of a certain radioactive substance is 20 days and there are 5 grams present initially. Find the time when there will be 1 gram of the substance remaining. Okay, so I have to tell you what the half-life formula is because it's a little bit different, okay? We still have our initial amount. Our base, it's going to be 1/2. That makes sense, right? Half-life, base should be 1/2. Our exponent is T over N. Okay, the exponent is T over N. T is still your time. N is not the number of times that it's compounded, because we're not talking about compounding. N is the length of the half-life. Okay, N is the half-life length. Now, I don't think, they're not going to expect you to know this one. Okay, this is not one that you have to memorize. But it's an exponential model, so I wanted to expose you to it. Okay, so there's your formula for half-life. So let's plug in what we know and what we're trying to find here. The half-life is 20 days, so they gave us that. That's N. There are 5 grams present initially. That's P. Find the time when there will be 1 gram. So that's our F of T. We don't know what time that'll happen, but that's what's on that side of the equation. We don't know T. We know N. So 1 equals 5 times 1/2 to the T over 20. First step, divide by 5. You got to get the exponential by itself. It would be nice if 1/5 and 1/2 could be written so that they have the same base. They can't. So we've got to use log form. Log, the base of the exponential and the base of the logarithm are always the same. We don't usually have fractions for bases, but it is possible. So we've got log base 1/2 of 1/5 is equal to T over 20. Let's go ahead and do our change of base. So don't forget that. And then what do we do to get our variable by itself? Multiply by 20. So I'm not doing anything different from last week, guys. I just gave it a context. Okay, we just gave the problem a context. We've solved these already. You're supposed to know how to solve these already. Y'all did well on the quiz. So 46.439 is T. What's our units? What's our unit on the time? Days. Okay, days. Anytime you have a real life problem, you need to put units with it. Okay, always include units when you have a real life application problem. All right, I got one more I want to show you, and then I'm going to give you plenty to practice with here. What number are we on? 6? No, we're on 5. Okay. Money is invested in an account that compounds monthly at a rate of 2.3%. How long will it take for the account value to double? So let's go through and label what we've got. We've got compounds monthly, so we know N is 12 at a rate of 2.3%, so R is 0.023. That's all they gave us. So let's try and set up our equation. We don't know our principal, so I'm going to move to my parentheses here. 1 plus 0.023 over 12 raised to the n times t, so n is 12. How long will it take? So that means t is my variable. But I'm missing two parts of my equation. I don't know how much I start with, and I don't know how much I'm ending up with. But what else did they tell me? Okay, so it doubles. So does it really matter how much I start with? No, it doesn't matter how much I start with. So if they give you a problem like this, and it's going to work out the same way every time, but I'm just going to start, I'm going to pick, I don't know, somebody give me an amount that we invested. Reasonable amount that we invested. 20 grand. Okay. That's fairly reasonable. I wish I had 20 grand to invest, but anyways. 20 grand. So if it doubles, how much do we end up with? 40. What's going to be the first step in solving this equation? Divide by 20,000, and what are we going to get? 2. It doesn't matter what you start with. If it doubles, this is always what's going to happen. You're going to end up with your 1 plus the rate over n to the nt is going to be equal to 2. So you don't have to know how much you start with, because if it's doubling, it's always going to do this number right here. All right, so our exponential is by itself. I usually don't do this. I usually leave this in this form, but since my variable's in the exponent, I'm going to go ahead and get that value. I'm going to go ahead and do 1 plus 0.023 over 12. And since it's a kind of nasty decimal number, I'm going to store that as x. Remember I showed you how to store values? Because I'm going to have to type that into my calculator here in a minute. I do not want to round this off. Because exponential functions are so sensitive, you do not want to round that off, so that's why I'm storing it as x. I am going to round it off to write it on my problem, but I'm going to keep it stored as x in my calculator. All right, so next step to solve for t. What do we do? Log form. Base of the exponential is always the base of the logarithm of 2 is equal to 12t, and then we divide by 12. So if we're typing this in, first of all, we got to do change base. Log of 2 divided by the log of that number I stored as x divided by 12. So 30.167, 166 equals t. I was looking at the next 7. What are we talking about here? Months? Years? Years. T is years. T is years. Unless that rate was in something, something else, but T is in years here. So just over 30 years it'll take for it to double if you don't add any money to it.